Hello everyone. Today I'm going to present to you in the topic of right-seed image-to-image translation using generative adversarial networks to improve video-right image classification. Let's start with why we have to do this work. First of all, rice is a staple food for more than a half of human populations. Moreover, rice is one of the most important economic crops for Thailand. But some varieties of rice are considered as weedy rice, which produce 80% less products compared with the cultivated rice. The most related research work to our work is Kitinan et al. And Asnan et al., which has been done the weedy rice classification model using rice images. Nevertheless, the images used in those research are captured in closed environment, which is not directly applicable in real-world situation. So the objective of this paper is to train the model which can translate rice seed images captured by mobile camera into DSLR-like images. For the literature, we start by looking at generative adversarial networks, which consists of two components, generator and discriminator, in which they resist each other. Then we take a look at conditional adversarial networks, which include class label into generative and discriminative process, in addition to vanilla GANs. And the last one to remark is image-to-image translations, which is the process of translating image in a specific domain into another domain. The dataset we use consists of 10 species of rice captured by 6 different cameras. The 10 species are divided into 2 main types, cultivated and weedy rice. Also for the cameras, we divided into 2 types. Canon 77D is DSLR camera and others are mobile cameras. We divided the dataset into training, validation, and test set. The test set is all images captured by iPhone 7 Plus. This has been done to test whether the model works on images captured by unknown mobile camera or not. Then the remainings are split into training and validation sets by 80:20 ratio. Next, the architectures of the networks used in this paper is adapted from CycleGAN. And the laws of all models which we are going to propose are formed using 4 types of laws: adversarial, cycle consistency, identity, and classification laws. The evaluation is done by comparing the results with the benchmark, which is the binary classification model that classifies between cultivated and weedy rice, with the same architecture as shown in previous slide. The model was trained on DSLR images and tested with validation and test sets. The test results on the validation set has 98.84% accuracy on DSLR images and 59.03% on mobile images. For the test results on the test set, the model achieved 59.79% accuracy. The good translator model means the translated mobile images, which should look like DSLR images, should have the higher performance than the mobile benchmarks. And the translated DSLR images shouldn't sacrifice much accuracy compared to the DSLR benchmarks. We have two domains of images which are mobiles and DSLR domains, annotated by X and Y respectively. The X with the subscript number is a subset divided by the camera used to capture them. The first architecture is also adapted from CycleGAN, which consists of a generator G, which translates the input images from any domains into DSLR, a discriminator dy, which discriminates real and fake DSLR images, and generators fk, which translates fake DSLR back to their original subdomains. The validation results of the model has been done both qualitative and quantitative ways, but we focus on the quantitative one since the qualitative is hard to measure. The quantitative results for the first model are shown on the table on the right. The accuracy on the DSLR validation set is dropped from the benchmark about 3%, but this comes with the improve on the mobile validation set by 24%. But the macro F1 score is not that high enough to use further. So we modify the first model a little bit by adding the classifier head, which classifies between the cultivated and weedy rice, into the discriminator model as a second model. The second model sacrificed more accuracy from DSLR validation set by 5%, but with significantly improvements on mobile validation set by 13%. Note that the macro F1 score for the DSLR validation set is dropped below 90%. So we decided to do more improvement by adding a classifier model into the first model instead of the classifier head done in the second model. The third model's performance on DSLR validation set is the best compared to the first and the second model. Moreover, the performance on mobile validation set is only a little bit lower than the second model. Although the third model seems to be good enough, we want to do some more experiments by changing the classifier on the third model by the pre-trained classifier model, which is our benchmark, into the architecture. The quantitative results for the fourth model is very high on all validation set. However, the qualitative results are not quite well, since the translated images look more crimson with the red border around the seeds. This is the qualitative results on the test set, same as before. The result from the fourth model does not look like the right seed images captured by DSLR camera. Others are good, but some of it may look like different seed from their original. For the quantitative results on the test set, the best model is second model with 90% accuracy and 89% macro F1 score. To summarize so far, we conclude that the second model is our best model, according to both qualitative and quantitative results on the test set. Moreover, we have seen that the fourth model is overfitting, since the benchmark model is used as a part of loss. And the last thing to remark is the qualitative results still be the problem. The suggestion is to add max comparison as another part of loss to reduce this problem. And that's all for today. Thanks for watching.